Thank you for the kind introduction, and I'm very happy to be here with you. Automatic analysis of visual data has transformed our world in countless ways. In some specialized domains, we can think about it as providing experts with an extra pair of eyes. And I'll start by going through the terms of this title, starting with visual analysis. The goal of visual analysis is to understand shapes through their geometries. And typical tasks are classification and retrieval, and edge detection and segmentation, and so on and so forth. But we also looked at tasks to which we call computational perception, where we try to teach the computer to perceive visual data as humans do, and not as what's in the image. And such tasks include saliency detection and memorability, which is which images do we remember and which we do not, and visual illusions, why they happen and how we can produce them. And we've worked on all these tasks in the general domain, where data is either surfaces or point clouds or images. And the methods we have used also vary. They may be classical, actually doing geometry, or deep learning. But today, I'll not talk about all these issues, but rather focus on specialized domains. When we talk about general domains, then usually to get good results, you have two legs. You're looking for a robust model, and you have to have sufficient proper data for your application. But what if the data leg is not that stable? Or in other words, in specialized domains, we assume that we do not have enough data, and we will never have enough data, either because of the difficulties in capturing the data, or because of privacy and ethical issues. And also, we need expertise to tag the data. It's not like send it to Mechanical Turk and let the world do the job, but you need to have experts, which make it very expensive to tag the data. In terms of the objects, we look at the objects typically lack clean and well-behaved geometries. Rather, they are braided and rugged and noisy and broken. And also, the data is not natural data, which means that it does not satisfy properties that are considered properties of natural data that algorithms use. And finally, in terms of balance, the crucial information often occupies very small portions of the data, the subtleties. And the data set may be completely imbalanced. Under this hood of specialized domains, we have been looking at three types of applications. The first, in the medical domain, when we look at chest X-rays and the reports that radiologists produce after the scans. We also look at what's called wilderness search and rescue, or WISR, where you're looking for people, for lost people in rugged and remote and uninhabited places. And finally, we look at archaeology. I'll start my talk with archaeology. However, at the end of the talk, I'll speak of the other two domains. Let me say that we're in different stages in the three domains. In archaeology, we have been exploring for the last 15 years or so. In medical images, this is a matter of 2-3 years. And in WISR applications, this is really, really new. Okay. So archaeology, the third term in the title. The first time we met archaeologists, this was in the cafeteria of Haifa University, everybody introduce themselves, and they say, hi, I'm this and this, Iron Age. Hi, I'm this and this, Hellenistic period. And I said, I am Ayellet Tal, the 21st century. And in some sense, this is the essence of this project, how to bring archaeology to the 21st century. And we'll see a variety of problems within archaeology that regard this core problem. But first, let me tell you what archaeologists do. And I'll tell you what archaeologists do from my point of view, the point of view of a computer scientist. And I do not think that archaeologists will share this view with me. And yet. So first, and also one thing to notice, we're looking at the type of sites where you find little remains, broken pieces, or little remains from old periods, and not at the sites of huge monuments of Greek and Roman cultures. Okay? So what archaeologists do, first, for a few weeks, a year, they actually dig. They go to the excavations and they do the digging. And then they have to document their findings in tech reports or in books. A core question in this domain is how to locate your findings in time and place. And finally, in parallel to all this, they attempt to do restoration, which means to bring the artifacts to the appearance they used to have before the disaster. Because usually in this site, something happens, some disaster, wars, or fires, or earthquakes, something bad happens. When we looked at all this, we said, sure enough, we know how to solve them. After all, these are problems that we do in graphics and vision. We just give them different names. So documentation is edge detection and domain transfer, and location is classification and retrieval, and restoration is puzzle solving and whole completion and recolorization, and so on and so forth. So we thought, okay, that's good, because we can, this was our vision. We just replaced these manual Sisyphean ways they do the work with our well-known algorithms, and the problem is solved. But little did we know. So why is it challenging? Because of all the reasons that, all the properties of specialized domains. We do not have massive data sets. In fact, they are very tiny. And even those tiny data sets are usually not public. You really need an expertise to tag the object. These are usually experienced archaeologists, not even PhD archaeologists. And the object, of course, slack and clean and well-defined geometries after lying underground for thousands of years. And the data is unnatural. These are artifacts. The crucial information is sometimes very tiny, only the relief on the artifact or some letter. And the data is imbalanced. Whatever you find, and you think you're lucky. So for all this reason, this domain exposes the limits of current graphics and vision techniques. Before I show you why, I want to say a few words about our collaborators. Over these 15 years, the way to bridge the cultural gap between archaeologists and us was to collaborate with archaeologists, and we added groups. So our long-standing group is the archaeologists who excavate Dor in Israel. And these are archaeologists from University of Haifa and the Hebrew University. And then we had the new collaborations with the British Museum and the Cyprus Institute under the H2020 European project that is called Gravitate. And these guys learned Salamis in Cyprus. And finally, our recent collaboration is with the University of Bern, where they study ancient Egypt. To understand the periods, I'll show you the periods of Dor. Artifacts in Dor were found starting at the Canaanites, at the late Bronze Age, at the 13th century. Dor is located halfway between Tel Aviv and Haifa, where I live and where I work, and it's a very strategic location. It has a natural bay, and before the invention of artificial harbors by the Romans, the only way to go from Phoenicia, today's Lebanon, to Egypt was to stop somewhere in the middle, and Dor, because it has this artificial bay, was an optimal location, and it has a few other strategic benefits. So after the Canaanites, everybody ruled Dor because of this strategic location. The Sea People, at the early Iron Age, the Israelites, these are the United Kingdom under King David and King Solomon. At the Iron Age, the Assyrians, the Persians, the Greek, Alexander the Great, and finally the Romans conquered Dor at 63 BCE and stayed there for 300 years. And these are the type of findings that you have in Dor. So this is a Phoenician pottery that was produced in Dor, but found in Cyprus. This is a beautiful Iron Age seal this is an early Hebrew script where it says Kohen Dor. Kohen, you probably know this last name, it means priest, the priest of Dor. This is a Hellenistic silver coin and a Hellenistic oil lamp. And this is from the Roman period. It's a drinking cup that is shaped like an African. And there is a little museum in Dor where you can see everything that was found over dozens of years of excavations. Salamis existed for more or less the same time. And you can see here really stunning findings, all date back 2,500 years old. Today they are distributed all over museums in Britain and also a few in Cyprus. And finally, I said the last collaboration is with archaeologists who study Egypt. These are Egyptian scarabs. I took this picture last year at the Metropolitan in New York City. So scarabs are amulets that are shaped like beetles. At the bottom of the beetle, you have all the nice information, okay? And they are found in large numbers in Egypt. To appreciate their size, you can see here, they're really, really, really tiny. Okay. So this is just an introduction to our domain, to our application. And now, remember the three tasks? We said documentation, location, and restoration. We will go through them and see some results that we have over the years. Starting from documentation. So once you find an artifact, it's highly important to document it in tech reports or in books. And of course, people do it in text, but also they do it through drawing, like this. Okay, so you invite an artist, a special artist, an archaeological artist, sometimes called a draft person, okay, who specializes in drawing archaeological artifacts, and he looks at the artifacts and draws what he sees. Okay, that's the common practice. And you can understand that this procedure is highly time-consuming and expensive, but also it is prone to inaccuracies of the artist and to the biases of the archaeologist who tell the artist what to draw. You may wonder, why not take a picture? So here's a picture of a Hellenistic oil lamp from Dor. And And if you look at this, it's very difficult to see what's in the drawing, what's the facial features, what do you see in here? So we thought instead, let's scan it in 3D. And the scan looks like this. So now it's much clearer. You can really see the facial features, you can see the hairdo, it's much more legible. However, it's still challenging to understand, and it's not as pretty as the picture, it's the drawing I saw you before. So we thought, why not draw the lines ourselves, but draw it on the 3D scan of the object. And prior to deep learning, we actually developed math to do these drawings. And let me say that unlike 2D edge detection, we are looking for curves in 3D, okay, on the surface, on the scanned surface. And we came up with a new definition of a curve that we call demarcating curve. To get an intuition to what these demarcating curves are, let's look at the surface to the left. So every point on the surface, locally, you can view it as a terrain. And as you see to the right, it's a zoom out of the brown rectangle. And like any geographic terrains, it has ridges and valleys, here in red and blue. And these ridges and valleys have exact mathematical definition. Archers go on the slopes between ridges and valleys and demarcate them. Okay. Mathematically, and I'm not going to go into details, but those who are interested, mathematically, a demarcating point is a zero crossing of the normal curvature in the direction of the fastest transition from convex, from valleys, to concave, to ridges. At the fastest transition, this is our direction, and we look there at the zero crossing and the inflection points. And if we add to this demarcating points we call it shading, it's like coloring. For every point, we give a color that depends on the curvature. At this point, you get this picture. So now we can compare. To the left, you can see an image of the artifact, and to the right, you can see our result. Okay? And obviously, you can appreciate how nicely you can see the facial features and the hairdo and all the decorations of this broken Hellenistic oil lamp. Let me show you another example. So this is Hellenistic handle stamped by an official, from which it's very difficult to read what's in it. But if we apply our algorithm, that's what we get. It says Marcia Artemisia, okay? And let's see, it's mu, and alpha, rho, sigma, upsilon, and alpha again. And together, Marcia Artemisia, the first word is the name of the official, and the second is the name of the month in the Greek or the Rhodian calendar. And remember that all that happens in 3D. Okay, so the archaeologist can manipulate the object as though they held it in their hand. And so you can see here an artist's result, not for the same lamp, but for a similar one we found in the books. And to the right, you see the two versions of our algorithm with or without shading. The problem with this algorithm, in the paper, I must say that you have the exact mathematical definitions, you have the algorithms on how to construct it on triangular mesh, and you have some proofs of how these curves relate to other curves known in the literature. But this solution, unfortunately, is not scalable because archaeologists very rarely scan their objects. And therefore, lately, we looked at the same problem, but in 2D, because images we can find. So you can see on top images of scarabs, of Egyptian scarabs, and at the bottom, you can see the results of our generative model. Okay? And just that you can compare, so the input is on the left column, and then you can have the manual drawings of the scarabs in ours, and you can see that our drawings, they're nice, but they're not as pretty as the artists. You can see it especially, I think, at the bottom, where the delicate texture of the ibex is not as good, and this is because an artist knows the field, and he just corrects and completes what's missing. But to the right, you can see the result of a state-of-the-art edge detector. Okay? So this is like the first example where you can see really the difference between general algorithms and specialized algorithms. Okay? And I'll get to this model later on when we talk about a different problem. So this was documentation. The next issue I would like to show you is called restoration. So recall, the goal of restoration is to reconstruct the appearance of an artifact as it used to be thousands of years ago. So that's our goal. Under this hood, there is a range of problems. For instance, the first problem is called reassembly. And the goal here is to reconstruct an object from its fragments. Okay. The second problem is called hole completion in our jargon, where the idea is to filling the gaps, filling the missing, the broken parts of an artifact. Another problem is reconstruction from drawing. When sometimes you do want to have the 3D artifacts, but unfortunately, once you find the finding, you document it, and you send it to storage rooms or to museums, and you don't have access to it anymore. But you always have access to the drawings. Okay. So in these papers, we looked at ways to reconstruct the three-dimensional object directly from the drawing. So it's like the reverse problem to what we've seen in documentation. Recolorization is another problem where the goal here is to bring the colors back. Sometimes we think about the great statues and columns of ancient Greek or Rome as being plain stone. But many researchers claim that this was not the case, that these statues were colored and vibrant and very beautiful. Only over the years, the pigments, very little of the pigments remains, and even those were taking off when cleaning them. So the question was, can we bring those colors back? And finally, another work we had is documentation enhancement. So you get an ancient document, and your goal is to clean it from its stains, from ink spills, and from other degradations that happen over time. We've worked on all these problems, but today I would like to highlight only this one restoration issue, which is reassembly. To get some inspiration to this problem, here's an image that I took at the basement of the British Museum. So apparently the basement of the British Museum is the real thing, okay? You have there drawers and drawers and drawers of artifacts. Most of them have never been displayed and will never be displayed. This is, of course, because we worked on salamis, these are the drawers of salamis. And some of these fragments are really, really beautiful. And you see that you could hardly glue them together. They really fit. So how is restoration done today? Like this, piece by piece, using glue. But if you make even a small mistake, a very small mistake when gluing, you're going to discover it along the way when it accumulates. And then you have to unglue and restart. So he said, OK, we have a different name to this problem. We call it in our community puzzle solving. So let's define puzzle solving. The goal of puzzle solving is to reconstruct an object from a set of non-overlapping and unordered parts. And there are many variants to this problem. But unfortunately, even the easier parts are hard. In fact, they're NP-hard. And yet, people have been working on this problem for many years and still work on this problem on puzzle solving. So we thought we had a plan. And in this plan, we thought to ourselves, let's study the general problem first, like everybody else envisioned, and then add properties that belong to archaeology. So what is the general problem in vision? In vision, they take an image, they cut it into equal part squares, and this is the puzzle. Now they have to put the squares back together. Okay. And so the first two properties we added was, and of course it was taken from archaeology, we still have these natural images, square parts, but now we said, okay, now we're going to have a few puzzles mixed together. Okay, so the pieces are mixed together, and also you have some missing pieces, because this is the situation in archaeology. And once we define this problem, these are the results. So what you see on top is the input that has 5,000 pieces. And these are the results of this algorithm, where it faultlessly reconstructed 5 puzzles out of it, where the poppy seeds, the black squares, are the missing pieces. Okay? Here's another example, a harder example. Now it has 13,000 pieces, and you see the output, 3 puzzles that, again, were reconstructed by the algorithm without any errors. And this is considered harder because you have lots of shades of white in this puzzle. OK, we thought we made a progress. And now we added an additional properties of archaeological data. First, that you have abrasion that create gaps between the pieces, as you see on top. Okay? Pieces don't stick together, which is very unfortunate, because all the other algorithms considered only the edges. Okay. Second, that you have color fading that creates spurious edges, which should be distinguished from real edges in the colors, because real edges are a good hint how to solve a puzzle. Third, that the set of valid transformations between every pair of pieces belong to a continuous space, unlike when you have square puzzles where every pair has only 16 possible transformations between them, but now it's infinite. And finally, as always, we have shortage of data. So we developed a new algorithm that specialized and took all the knowledge into account. And these are the results that we have. Okay. Let me show you a few more results, and more results. And maybe 3 weeks after we put this paper on archive, a friend of us from London sent us this piece from the Times of London. And it says, AI's answer to Indiana Jones picks up the pieces from broken treasures. So this was, and of course, after the Times of London, it was published everywhere, in La Repubblica in Italy, and in India, and in Cyprus, and in all kinds of places. But the nice thing about this, article in the popular media was that they never talked to us, okay? They just interviewed archaeologists, which was nice. We were interested in the article, and the archaeologists said, yes, this is a very important problem, and they praised the result, and so on. So now, again, I would like you to compare. This is what we managed to do with General Puzzle. More than 13,000 pieces in no time, in a few minutes, okay? And in archaeological, but our algorithm didn't work at all for archaeology, so we developed a new one for archaeology, and even for the new one, we managed to solve whatever, 30 pieces. So that's the gap between general algorithms and specialized ones. And I think you mentioned it as well. Like specialized algorithms need knowledge, specific knowledge, and even then, it's challenging. Okay. And now, I'd like to go to, so we've seen documentation and restoration, and I'd like to look at the last task, which is the location. Okay. So when you find an artifact, you have to locate it in time and place. In time, many times chemistry suffices, okay? But in place, this is what people are doing today, okay? They are leafing through thousands of pages in relevant publications, okay? So to start with, you have to choose which publications have a chance to find something like yours. So you do pre-selection, and then you can spend years looking through this. Actually, sometimes really years. Sometimes this is considered a PhD, okay? Looking for similar stuff. And this is at the core of archaeology, because when you find these locations, you learn so much about commerce, about cultural relationships, about wealth. You answer so many questions, so this is really a very important part of this discipline. To understand how difficult it is, I'm going to give you a test. Okay? Ready? Okay. So this test is all from the scarves, from a last collaboration. And I'll show you scarabs, and you'll have to guess. So in these scarabs, what do you see? A bat, a bird, or a beetle? What? Okay. It's a beetle. Okay? You said a bat. Okay. And how do we know it? Because we look at the image. And now you believe me, it's a beetle. Okay. You have another chance. What's this? A lion, an ibex, or a horse? Ibex. Good. Here's an ibex. Very good. What's this? Lion, ibex, horse. Horse. Lion. Horse. Majority horse, a few lions. Okay, lion. Now you can see it's a very nice lion. And finally, what's this? You have three options: human, snake, or bird. What? Human? Bird. Now you see. So let's conclude. You failed the test. Okay. And this shows you the challenges, how difficult it is, even for people who are not experts. Okay. And to add to these challenges, items of the same class lack consistency. These are all lions, but they come from different artists, from different workshops, from different historical periods, okay? And let alone that many times we want to cluster by period, okay? So we developed a model, a deep learning model, and this was the key idea. The key idea was exactly the test that I gave you. That sometimes images are associated with drawings. And although the drawings are not the exact edges, and they're not aligned because you saw how they were drawn, okay? They're very beneficial. Both modalities have the same features, the same global features, but they're more enhanced in the drawings. So let us use it in our deep learning model. So this was the core idea of our model. And then, once we train on both images and drawings, but of course, during inference, we use only the images. And to see this, look at the top, when you have only the artifact, okay, then, and we look at the localization map of our deep learning model. We did not train here on the drawing. Then you see that the localization map shows you that it focuses on the torso and the legs. But on torso and legs, you cannot distinguish between lions and ibexes. On the bottom, you can see what would happen to our model. What's the localization map when you give it both the drawing and the artifact and the image. And here, the focus is on torso and the horns. And in fact, the horns are exactly the features that distinguish between the two classes. And as a side benefit, because we train our model on drawings, as well as on the images, this enables us to generate drawings. And these are the drawings that I showed you before, okay? The result that I've shown you before. So the contribution of this really recent paper, it's from 2024, is the following. So we propose a semi-supervised method that is also multimodal. And it's semi-supervised because we don't always have the classification. Okay? And also, we have an end-to-end model that classifies and retrieves both by shape and period. If you look at this image at the bottom, given the input image, it can classify it and say this is an ibex. And here in the, you taught me how to do this. Yes, you can see here that the sum of the objects from the class of ibexes, they differ from each other. And it can also classify by period. It dates this artifact to the late Iron Age. And you can see that here, this is the class of Iron Age, of late Iron Age. The variety is huge. Okay? And it also knows how to generate. So this is an end-to-end model that does everything. Let me go very briefly through the model, okay? Very, very briefly. So this is a model, and it gets as input both images and drawings. Most of them are unlabeled, as you see in the middle, but some are. And then every modality goes to its own decoder, okay? To its own decoder and to a fully connected layer, and it learns how to classify separately for images and for drawings, okay? But now, the major idea the key idea of this model was to teach actually the image to behave like to learn from the drawing. And this is why I marked here the similarity. So we have here a similarity loss in order to bring the two embeddings together. And finally, we have a decoder that learns how to generate a drawing, and a loss function that compares and the drawing and the ground truth drawing with the generated drawings. So this is briefly. And last but not least, we have a new data set of images and drawings of scarabs, of Egyptian scarabs. It's called CSSL, the Corpus of Stamped Seals of the Southern Levant Dataset. Okay, you can understand that we didn't give this name. And this data set was collected at the University of Bern from 7 different archaeological groups who have this data for their own research. It's not for us. So they dig in different places, they have different artists, and they're willing to share it with us. And this is the first data set in archaeology that has both drawings and artifacts of any kind, not only of scarabs. In addition, and so this data set has more than 6,000 pairs. 1,000 of them are classified. The others are unclassified by shape. And I would say there are a few other archaeological data sets that are published, not of scarabs, but of others, of coins, of hieroglyphs. But they're limited in their preservations or in their variety, which means some data sets, the artifacts are very well preserved. In others, they're not very well preserved, but the variety of within a class is not that big. And this is the first one that both are challenging. And also, we have a secondary classification into periods. And you see here 3 periods. 3 bronze periods, 2 middle bronze and 1 late bronze, and 2 Iron Age, early and late. And this spans hundreds of years. So lots happened in hundreds of years. When we use a variety of general purpose algorithms, and on each of them we added our model. And you can see here that for each of these general models, we improved the ability to classify or to retrieve objects. So what have we learned until now? First, that archaeology really exposes the limits of current vision techniques. General techniques do not work well. We saw it in restoration, in puzzle solve it. We saw it in documentation, in edge detection, and we saw it now in classification. So you must come up with specialized models if you want to solve these problems. Second, we need extra domain-specific knowledge, not only for tagging, but also even the drawings gave us the extra knowledge. It was implicit, but it was the extra knowledge of the artist and the archaeologist. And so, because those will guide you to what you have to concentrate. And finally, this problem has lots of facets. It's not enough to come up with models for analysis and generation, but we also have to look at the data, and I showed you examples of a new data set that can advance the state of the art. And we have to question the evaluation that people are using, but, and we did it on a few problems, but instead of going into it in archaeology, I'll talk a little bit about evaluation in the medical domain. As I said, this is our really long-standing project. We did it for so many years. But lately, we started 2 new projects, one in the medical domain and the other in the wilderness, and I'll show you. In medical domain, we already published. In the wilderness, we're just starting. Let me show you these domains, but before, let's go for the properties of specialized domain that I showed you at the beginning. So this is archaeology, and we saw the data sets are tiny, and expertise is needed, and the objects are really bad and non-natural. The crucial information is really in a few lines, and the data is imbalanced. But the same is true when we're looking at chest X-ray. We do not have massive data sets. In fact, for evaluation, we have 200 pairs, but there is one bigger data set. Expertise is needed. You do have to get the knowledge from radiologists. The data is unnatural. These are X-ray. The objects are organs. The crucial information occupies small portion. It's usually the diagnosis. And sometimes this diagnosis is not even concentrated, but it's all over the place. And the data is imbalanced because if you look at all these images, most of them, thanks God, are normal. Okay? So, and the same for WISER. So, we don't have massive data. They are very tiny. The idea here is to look for lost people. And the expertise is needed depending on the data set. The data is unnatural. In fact, it is natural. This is nature. But we're looking for the small portions of the unnatural ones, and we're doing it usually not in images, but in LiDAR or SAR or other scanning devices. And the object, usually, if you look at point clouds, they're irregular, they're occluded, they're not. I'll show you examples. The crucial information occupies small portions. You have a big desert, and there is a person or something that belongs to the person that indicates the person was there, and therefore it's completely imbalanced. So I'd say if we look at these 4 facets of the problems, we looked at analysis in 3 facets, in generation in two of our domains. For the data sets, we have some data sets in all 3, and evaluation, we have some evaluation metrics in archaeology, but I'll say a word about this for the medical domain. So let's start for the medical domains. So chest X-rays are one of the most commonly performed medical imaging procedures, where 70 million scans are performed annually in the US alone. And it enables diagnosis of a wide range of pathologies and abnormalities in the lungs, in the heart, and in the chest bones. And during post-scan, a medical report is written by a radiologist. To the left, you see the X-rays, and to the right, you see a report. And this report summarizes the findings, not only the bad findings, but also the good ones. It says the lungs are in good shape, they're good size, and so on. And so when we started on this, it was 2023, we worked on analysis, where we had 2 tasks. The first task is called phrase grounding, which is you get an image and you get a phrase from the report, and you have to locate this phrase on the image. Okay? So this is the task. The second one is text-to-image retrieval. That is, I give you a report, you give me the X-ray image, or I give you the X-ray image, you give me a report from the data set. This was the first paper. And then, this year, we have 2 papers on generation. That is, you get only an X-ray image, and you have to generate the report yourself. Okay. And the interesting point about the generation is that because in medicine people are not that generous in releasing their data because of privacy, because of ethical constraints. So what we chose to do was to look at unpaired domains. That is, you get one data set only of images from Spain, and then you get another data set only of reports from New York, okay? And these are not at all the same patients, okay? So this was the setup that we had for these papers, okay? And we show that we managed to generate pretty decent reports in this challenging setup. And finally, what I promised was to say a few words about evaluation. Okay. How do people evaluate the results? For generation, okay? For report generation, because this was the two last papers. And I'm sure that everybody who works on some special domains see these problems. So what do people do in the general domains? They do it like captioning, okay? You get an image, and you generate a caption, and you compare your caption to ground truth captioning. So in this domain, people decided to do the same, okay? To use all those known metrics, okay, like blue and others, okay? But this does not give you the story, because two different reports can say exactly the same. They differ in style, they differ in doctors, but they can say exactly the same. Okay? For instance, what you see here on the left are two different reports that say, essentially, I'll summarize it for you, everything is normal, okay? But they say it very differently. So the regular metrics are going to fail. And you can see it here at the bottom, okay? Another type of metric that people use is to say, okay, we don't want to do only text, so instead we will just look if the same pathology exists in the same, in the two reports. So the metric is based only on having the same pathology. But this is also not enough, because just knowing the pathology doesn't give you a lot of information. Where is it? What's the size? What's the severity? And so on. So you see here to the right, okay, you can see here that we just exchanged one word, which is, it's in the left and not on the right, which may be disastrous, okay? And all the non-evaluation metrics were very happy about this, because the text is almost the same except for one word. And imagine, and imagine if this word was exist and does not exist. And so in this paper, we came with a new evaluation metric that suits the domain and takes into account the knowledge of the domain. I will not get into details. It was last month in NeurIPS. But the idea was that if you want to compare two reports, you have to do it through the image, okay? They are not independent. And finally, our last application is called Wilderness Search and Rescue, or WISER. So here we want to search and rescue in remote, rugged, and often uninhabited wilderness. So the goal is to do detection, which is localizing and classifying objects in the open environment. And we want to localize humans, and we want to localize belongings of humans. The current data sets are tiny, they're in 2D. And the problem in 2D is that it depends on lighting. You cannot look for them at night. It depends on the weather, if you have fog or rain, and if they hide below the foliage, and so on. So our solution was the following. Take a LiDAR sensor and install it on a drone, and then fly your drone. Okay? Fly your drone and collect information. And because it's LiDAR, it can operate in any lighting conditions, including dusk and dawn, and it can do pretty well in various weather conditions, and it can even penetrate foliage when it's not too thick. And we have the first aerial LiDAR data sets. We recorded 5 hours, and the tagging was a nightmare. You can see here 67K bounding boxes of objects. And because there is no model that runs on it yet, what we did is we took 9 state-of-the-art detection algorithm models that operate on autonomous cars, and we modify it to suit our data set. And you see here the results, okay? So humans, we could locate only 50% of the time, approximately. And human indicators, approximately 70%, but mostly because we have tents and cars where we took these images. But if we didn't have the big things, only the little object, then it would do much worse. And this is how it looks. So you can see how hard it is to tag anything in this data set. Here, this is a tent, so you can see a little bit more. But this thing here, I read it because I would never know. Okay. Let me stop, and I'll tell you this is a sitting man. Can you imagine? Okay. And here are more of our data set. Okay, so you see that the cars are big, and you can really see them. But the other artifacts, whatever they are really, really, really tiny, and they make the problem much harder. Okay? So let me conclude. Okay. So we saw 3 applications that, in addition to sharing common characteristics, they aim to do good, both archaeology and medical analyzer. And these applications indicate that when it comes to expert-level intelligence, we, technology, are not yet there. Okay? When you do not have zillions of data, our models are not going that great. And we saw it in a variety of applications. So, second, you should integrate any domain-specific knowledge available, anything. Even if it takes you to work only on unpaired data, because you don't have enough data in paired. If you can use other modalities, whatever you have, put inside your model. And finally, as I said, you have to re-examine all facets of your problem, the models, the data sets, and the evaluation metrics. One question I cannot yet answer is whether the experience we gained from archaeology help us in our other domains, okay? Obviously, in the general sense, it does, because we understand the problems, we understand what we need to add. The students talk to each other, but it's not like we have like a nice model that we can put inside the various applications. And I'll end with thank you. So you can see that the number of students I have in archaeology is large, but on the other domains, small than you. It's going to grow. And we collaborated with various archaeologists and with partners, and lots of agencies gave us money for that research. Thank you.
Yeah, many thanks for this great insight into your application domains and your incredible work. I think we all felt your fascination for archaeology, and I think that is what many of visual computing researchers is driving. I mean, I love it to learn every day something new with working with domain scientists, and this is so important for our work. Yeah, so other questions, please. Yeah.
So, first of all, thanks for your talk. I found it easy to understand, even being a non-expert. So you talked about the training data and how little the data sets were in the applications you talked about. And my question is about your model that generates the images from coins from this CSSL corpus. So you said this is a pretty small data set, but still you had very good results. Can you give an intuition why you still got that good results, even though you only have so few data?
Because I think the point is that the knowledge, our algorithm suits the knowledge. It's like, what's the difference between our general algorithms that know everything and a child? So a child, you show it a few examples, and it generalizes, okay? Because it has priors. That's the reason. The child has priors, okay? And you don't have to show it in order to learn a cow, you know, a zillion cows with all kinds of shapes and textures. Okay, you show it 5 cows, he knows how to do cows because he has priors. The idea of these models that they have the priors, okay? They have the experts in them, okay? And this is why the general algorithms did not work, because these models, the small models, the priors this is my intuition, help them generalize rather than memorize.
We have a question there. Huh?
Thanks as well for this great and inspiring talk. I'm here.
Here.
So, you talked a lot about the domain of archaeology, but also tapped onto other domains and talked about the importance of really capturing this tacit knowledge of these domain experts and that this tacit knowledge really flows into the algorithms. So when I look at this visual computing field in general, we rely very, very often on such tacit knowledge from the domain experts. And I have the impression they're flowing very often directly into these models, into the algorithms, into user interfaces. Have you found a way or an idea how we could capture that knowledge maybe in a somehow standardized or structured way to make exactly all these interviews, these findings somehow accessible for the next research collaboration for science in general? Because I think we're doing so much work here to actually capture all this knowledge from these domains, but I think this task keeps repeating very often, I think.
So the question is whether I know how to extract this knowledge.
Yeah, no, you managed to extract it, but have you found a way to formalize it in some way as an intermediate semantic layer, kind of, right?
So unfortunately, we did not. And the interesting thing that I do not believe even that the archaeologists knew. Let me give you an example. When we labeled the scarabs, okay, so at the beginning, archaeological students did that. And then their professor relabeled it, okay? It's that deep, you know, to know what it is. And these were PhD students. So we probably need so much experience to do that, and we do not have it. Although I must say that at the end of the project, my student did pretty well with tagging. Okay, so somehow he got it. He was on the phone all the time with this Swiss professor. Okay, all the time because, so at the end, he somehow knew how to do it, but I'm not sure I know how to extract it. They do have some guidelines, you know, we are looking for this age or that age, but I don't have it. But that's a good point. You should do it at some point, yeah.
I have a question there.
So thank you for your presentation. You solved a great deal of problems, especially there in the field of archaeology. But I was thinking maybe the archaeologists that you work with, maybe they also argue that some of these Sisyphean tasks that you speak about, they have a value in the field, how they deal with the materiality of the object itself and how this informs their interpretation of the past and so on. So I wanted to ask you, is there anything that you think that is lost by, you know, replacing all of this labor with algorithms and information?
In their domain. So I think, maybe in many specialized domains, you need to have somebody who wants this thing. So in archaeology, this means to find archaeologists who like technology, you know, who really, you know, want this change. So for instance, in our last collaboration, Stefan Brunner, that's the name of the archaeologist, is there. He really is so enthusiastic about this. For him, we built a special interface where he puts a scarab and he gets all and he retrieves the most similar scarab, and he was so excited about that. Okay, really. And so I think people are slowly going to get there, but it takes time. You know, it takes time to get into their way of work and to change it. You need to have patience. So the groups we worked on, and by the way, one of them was supported by the H2020 EU, and they insisted on having both technological groups and archaeologists, okay? They insisted on this because they understood that this is the only way that things will sink into the domain.
Any more questions? Yeah, over there. That's the last question.
Thanks for this talk. In digital humanities, there's a distinction between close reading and distant reading, or close viewing and distant viewing, respectively, when it comes to visual objects. So I just wanted to check if I understood it right, that you focus on close viewing, looking at single objects, individual objects, mainly with VRVis methods, or if you're also working on methods where you can zoom out, basically, and look at whole collections of archaeological artifacts.
On single objects.
Sorry?
Single objects.
Yes.
Not a full collection.
Do you maybe know of any other established systems that would allow to do that with archaeological objects? Sort of scalable reading or viewing?
I'm not sure. I'm not sure I understood.
You did it, yeah, but maybe you can repeat the question.
Okay, so I was just wondering, it was my perception that archaeology is largely focusing on individual objects.
Yes.
Yeah.
And there is a lot of intelligence directed to, you know, detecting shapes, understanding single objects. But in digital humanities, there is also this working area where you look at whole collections of large objects, like, for example, the British Museum collection you showed, thousands, millions of objects. And then you can also do visual reasoning, obviously, on distributions in space and time, and so on.
Yeah, I think they usually work on individual and the distribution. Maybe, I don't know, maybe they do it. I'm not sure, but usually they work on a very single one, you know, until they find an object. They're so happy about it. You see this, but this is, you know, was collected over so many years. Usually you go to excavation, you're very happy if you find a few. So you put all your patience, but maybe it's worth, you know, to look at the distributions.
Okay, I think we have to stop here at this moment. I mean, all speakers will be around. You can approach them. We invite you all to to a lunch today, and we come back at what time? 1:30. 1:15. Yeah, so, and then we continue. Thank you all. Thanks.